For the video today, we're going to take a look at slopes. Specifically, we're going to look at slopes of parallel and perpendicular lines. So let's think for a second about what the slope of a line is telling us about the line. If I look at line Q here, the slope of that line is telling us essentially it tells us how that line is kind of tilted, if you will. You've probably learned about slope being referred to as rise over run. You've probably learned about the idea that slopes can be positive or negative or zero or undefined. For instance, if we look at line Q here, we know that it has a negative slope because as it moves from left to right, it's moving downward. The rise over run idea is that a slope is kind of a comparison of as I move from one point to another point on the line, how much am I moving up or down versus how much am I moving left or right? And that kind of helps us determine the numerical value of the slope. But in terms of what slope really means, it's all about how the line is kind of slanted or tilted. If we have, for instance, if we had a line that looked like, I'll use this color here, we had a line that looks like this, that line clearly is tilted differently than line Q is, and so it would have a different slope. It still has a negative slope, but it's not tilted as much. It's kind of more flat, if you will, so it would have a different slope. So if I look at two lines that are parallel to each other, we can kind of tell that if they weren't tilted in the same way, then at some point, maybe not in the part of the in the part of the picture that we can see, but since lines are going to continue forever, if they weren't tilted the same way, then somewhere they would eventually cross each other, right? If they weren't tilted the exact same way. But if they are tilted, slanted, if you will, the exact same way, then we can see that they're never going to cross, even as they would perhaps get longer and longer and longer, even as this line Q got longer and longer and longer, and this line P got longer and longer and longer. If they're tilted the same way, they're never going to cross. And of course, we know in geometry that means that they are parallel. So if you put all that together, you can probably identify how we're going to finish the sentence here that makes up theorem 2-13. It says two non-vertical lines are parallel if and only if their slopes are equal. Their slopes are equal. And I'll talk in a second about why it specifies non-vertical lines. We're going to get to that down here. So, and hopefully that kind of makes sense after I talked for a few seconds about what a slope tells us about a line. That if they're parallel, they're never going to intersect. That means that they're kind of slanted and tilted the same way, which would mean that they have the same slope. So to kind of come over here and finish out what it says in our kind of the diagram portion of this theorem, if P and Q are both not vertical, then the slope of P equals the slope of Q. Now, it says non-vertical lines, and there's a reason for that. If you look at lines P and Q here, I don't know numerically exactly what their slopes are, but I know that they're negative, like I said, because they're moving downward as they go from left to right. A positive slope would look maybe something a little bit more like this. This line here, we can call it line L. It would have a positive slope because it's moving upward from left to right. A line that's flat, like say the x-axis, it has zero slope. Its slope is not positive, it's not negative, it's zero because it's flat. And then a vertical line like y, like the y-axis, has a slope that is undefined. And since that number, since that's not really a number, an undefined slope isn't really a number, then this definition wouldn't really work if we tried to include vertical lines in it. If we just said two lines are parallel if and only if their slopes are equal, well, what about vertical lines? They don't really have a numerical slope that can be equal to something. So we have to kind of build in some way of saying that, all vertical lines are parallel. And so that's basically exactly what we say. Any two vertical lines are parallel. So we can see in this diagram over here to the right, if P and Q are both vertical, then P is parallel to Q. Okay? So slopes that are parallel lines have slopes that are equal. If two line slopes are equal, they're going to be parallel, and all vertical lines are parallel to each other. Now, what about perpendicular lines? How are the slopes of perpendicular lines related? Well, if I just look at this diagram, I can at least say something about their slopes. I know that if P and Q are parallel, then one of them if they're perpendicular, one of them has a negative slope and the other one has a positive slope. So we can kind of already see that their slopes are definitely not going to be equal. One's negative and one's positive. What relationship do they have to one another? And what we say is that two non-vertical lines are perpendicular if and only if the product of their slopes is -1. Now, product means that we're going to multiply their slopes together. So if we take two lines, we multiply their slopes together, and we get -1 as the result, it tells us that those lines are perpendicular. Now, another way of saying that, we could also state that as two non-vertical lines are perpendicular if and only if their slopes are opposite reciprocals of one another. Either way is a fine way of thinking about the relationship between the slopes of perpendicular lines. We can either look at them and say, hey, they're going to multiply together to get -1, or their slopes are going to be opposite reciprocals of one another. And I'll just show you real quick why this is really saying the same thing. Let's imagine that the slope of Q over here, let's say Q has a slope of, I don't know, it looks to me like it's a positive, maybe it's up like a +3/2. And then line P has a slope, if it's perpendicular, if they're going to make a 90-degree angle, one way to look at it is the slope of P will be an opposite reciprocal of this one. Well, the opposite part means it's going to have an opposite sign, so we'll say it's negative. The reciprocal part of that means that the fraction version of the slope is going to be flipped over. So whereas Q had a slope of +3/2, P would have a slope of -2/3. Now, if I multiply these two numbers together, take a look at what happens. If I take -2/3 times 3/2, first of all, I'm multiplying a negative number times a positive number, so I know that result will be negative. And then when I multiply fractions, I just multiply numerators together, so 2 times 3 would give me 6. And I multiply denominators together, so 3 times 2 will give me 6, and that'll be -1. Okay? So perpendicular lines have slopes where the products are -1, or we can say their slopes are opposite reciprocals of one another. Now, just, again, because a vertical line would not have an actual numerical slope, we have to kind of put on an addition to this theorem where we say a non-vertical line, I don't want to say a non-vertical line. That's not what I meant to say there. I want to say a horizontal line, specifically a horizontal line and a vertical line are always perpendicular. So over here, if I look at P and it's vertical and I look at Q and it's horizontal, then P is perpendicular to Q. So parallel lines have the same slope, have equal slopes, but perpendicular lines have slopes that are opposite reciprocals, which means that when I multiply their slopes together, I'm going to get -1.